The 1-bit full adder is a crucial precursor to all modern electronic computing devices. It is a combinational logic device that takes in 3 1-bit binary digits as input and returns the sum of these numbers as a 2-bit binary number in its output. The less significant bit in the output is known as the sum, and the more significant bit is known as the carry. By cascading multiple 1-bit full adders, we can construct higher bit adders that are capable of adding 2 numbers with an arbitrarily large number of bits. Before going into the design of a full adder, let us take a quick look at its younger sibling, the half adder. Like the full adder, the half adder has a sum and carry in its output, but only takes in 2 binary digits as input. For a half adder, the carry will be 1 if and only if both of the inputs are 1, since 1 plus 1 equals 2. This corresponds to a logical AND gate. Now, let's look at the sum. It will be 1 if either of the inputs are 1. However, if both of them are 1, the addition will be carried over to the next significant bit, leaving the sum as 0. This corresponds to a logical XOR gate. We will now build on our half adder design and transform it into a full adder. In essence, we are adding in a third 1-bit input. This time, let's begin with the sum. Notice that the third input is at the same level of significance as the sum from a half adder. Hence, to find the sum of 3 inputs, we can simply add in a second half adder, which has as its inputs the sum from the first half adder and the third 1-bit input. The 3-input sum will then be the sum from our second half adder. Now, consider that for the carry output to be a 1, we need at least 2 of the inputs to be a 1. From our half adder design, if both of the first 2 inputs are 1, the first half adder's carry output will be 1. However, if only one of these inputs is 1, and the third input is also a 1, the second half adder's carry output will then be 1. In all other cases where only one or none of the inputs is 1, both of the half adders will have 0 as the carry output. Therefore, as long as either of the half adder's carry output is 1, the overall carry output of the full adder will be 1. Since the case where both of the half adders have a carry output of 1 cannot occur and is irrelevant, we can use either an OR or an XOR gate for our full adder's carry output. In this case, we chose to use an OR gate as it is typically simpler and less expensive than an XOR gate. At the gate level, this is what the schematic for our 1-bit full adder looks like. Let us now take a look at our physical full adder prototype. It consists of a total of 3 integrated circuits, the 74HC08, 74HC32 and 74HC86, which correspond to AND, OR, and XOR gates respectively. As each integrated circuit actually consists of 4 channels of the logic gate, we were able to reuse the AND and XOR circuits. Also included are 5 pull-down resistors that tie the inputs and outputs to a logical low, and 2 red LEDs which indicate the sum at the top and carry at the bottom. We used the field programmable gate array module to help us test the functionality of the full adder. It is able to automatically cycle through all 8 possible input combinations and compare the output of the adder to that of the desired truth table. Here it is in action. As can be seen, the full adder passes all 8 test cases by producing the correct output for each input permutation. The full adder can also be manually tested by toggling the switches on either the field programmable gate array or on the adder itself.